Okay, so hello once again. Let's officially start our quantum computing workshop, QSilver36. My name is Pavel. I'm one of the organizers. Uh, I'm currently the chairperson of the board of QWORD, which is an international organization that prepared the educational materials for you. I will tell you more about QWORD in the next slides as well. I'm also the coordinator of QPoland, the local Q cousin of QWORD here in Poland, which is the one of the organizers of this workshop, and I'm the CEO of Quantum AI Foundation, which is a legal body behind QPoland as well and behind this workshop. So it's a non-profit organization from Poland. So we'll have 5 days of classes starting today. The next one will be on Thursday, then in the next week on Monday, Thursday, and Friday. We'll start at 6 p.m. Oh, sorry, it should be UTC +1, so it's a time in Warsaw. So I'll fix it. I believe that on our website the time zone is correct. The instructor is Przemek Michałowski. Przemek is already with us, and we have 5 mentors: Adam, Miron, Saif, Ashwani, and Pak. I know that at least some of them are already with us. All the nice graphics were prepared by Agnieszka, our graphic designer. I sent you a link to our workshop materials in the invitation email. There's also a link on our Discord server. So the Discord is our main communication platform. So if you have any questions, feel free to just ask on Discord. During the lectures, you can also ask your questions here on the chat of Zoom, and Przemek our instructor Przemek or one of our mentors can try to answer your questions. So by default, the lectures will be conducted on Zoom, so the link will be the same every day. If there are some technical issues with Zoom, we'll try Discord. It was also announced in the invitation email, but just to let you know, you can receive a certificate after solving the quizzes and assignments in Canvas. So Canvas is the QWORD's platform for the homeworks, for quizzes, assignments that you could do or you should do just after the workshops. We'll send you the invitations to Canvas just after this talk. So the invitations will be sent to your email addresses that you used during the registration. There are different deadlines for completing different quizzes and assignments. So in each case, there are at least 2 weeks after the release of the quiz or assignment. They are set in Canvas, so after joining Canvas, just please check the deadlines. So not all homeworks, not all quizzes and assignments are available now. Some of them will be released after the next days and the next sessions. Okay, maybe just a few sentences about QWORD. So it's a global network of individuals, groups, and communities collaborating on education and implementation of quantum technologies and research activities. So QWORD prepared these educational materials that we'll use during the workshop. So you can follow our profiles, join the QWORD Discord server, subscribe to QWORD's YouTube channel. There are several projects that are led by QWORD. So QSilver is one of our workshops, so it's an intermediate level workshop. It's not an introductory level workshop, so we assume that you are not a beginner, that you already have some knowledge and good understanding of the fundamentals of quantum computing and some good experience with Python and linear algebra at least. And you know the basics of quantum computing corresponding to the material of QBronze. So QBronze is our introductory level workshop. And I know that most of you have already participated in one of the QBronze workshops, and many of you have received a certificate after QBronze workshops. We also organize some hackathons, QIntern program, which is a program for online research internships in quantum computing. And in general, in QWORD, we develop the whole curriculum of quantum computing materials. QPoland is one of the Q cousins in QWORD. It was one of the founding members of QWORD actually in 2019. together with four other groups from four other countries, we established QWord, and currently we have more than 30 Q cousins in different countries. So as QPoland, we also have our social media profiles and mailing lists and Discord server, so you can join. You can subscribe to our newsletter as well, which is a monthly newsletter with curated news from the quantum world. So here are the links. I will later share the slides for you, and the links are also available on our Discord server. So I invite you to join, of course. And a few words about the Quantum AI Foundation. So it's a non-profit organization um, that I founded a few years ago, and our goal is to support education, research, and collaboration in science and new technologies, in particular AI and quantum computing. So we also organize multiple initiatives. If you want, you can also donate and support our activities, but it's not mandatory. This workshop and all our activities are free for participants. So this is one of our goals, to democratize access to the education in quantum technologies and contribute to the development of the open global ecosystem in quantum technologies. So I wish you a good workshop, and thank you for your attention. If you have any questions about the organization of this workshop, I can try to answer now, or you can also ask me some questions later on Discord or on the chat. So let's check the chat now. There are some questions about recording, but I have already answered. Yes, the recording will be available. There was a second session, 26th. I will double check the date. I believe that it should be 26th. Sorry, so if there was a 25th here on the slide, then there was a typo. The second session is on 26th of February. Yes, thanks, Park. All right. A link to the Discord server. Thanks for sharing. It seems there are some problems with the link, so I will try to send another link. So it should be valid. So if you have some problems, based on our experience, it may mean that there are some problems with your Discord account, but we can try to generate another link to the Discord server. Okay, so I will soon just paste another one here on the chat. Are there any other questions about the organization of the workshop? Okay, I will stop sharing my slides now, and I will try to just generate a new link to the Discord. Okay, I've just pasted another link. Let's check if it works for you. And I see that Pack is not streaming. So Wojciech, if you have problems with this link, it's possible that there are some problems with your Discord account. I'm not sure if we'll be able to help. I can try to generate another one, but based on our experience, it may mean that there are some problems with your Discord account, or maybe some other technical issues. So let me just generate another link. Okay, I've just pasted another link, and I see that Wojciech has managed to do it. So add server, yes, pass the link directly. There can be one more issue. So on Discord, there is a limit for the number of Discord servers that you could be a member of. As far as I know, the limit is set to 100. So if you already have 100 Discord servers, if you're already a member of 100 Discord servers, in the free version of Discord at least, you will not be able to join as well. Okay, good. Pasting the link worked. All right. Are there any other questions regarding Discord, the organization of the workshop? And by the way, did all of you receive the invitation email? Because there were also some useful information about the installation of the environment. And there was also a link to this Discord and Zoom. Okay, if you haven't received the invitation email, please contact me on Discord. Okay, so yeah, if there are some other questions or issues, just let us know here on the chat or on Discord, and we'll try to help you. And if there are no other questions, I will just give the Zoom to Przemek. So Przemek, if you're ready, the Zoom is yours. And let me just check the settings. I'm not sure if you are able to share your screen now. If not, then yes, you should be able to.
Should be OneNote, yes?
Yeah, you can.
Okay. That's great.
You should be able to share your slides now.
Okay. Because can you see, like, I'm drawing a circle in OneNote?
I can see it.
Yes.
Okay, great. Okay, so I think we may start. So, hi everyone. Thank you, Paweł, for great introduction. My name is Przemek Michałowski, and for the next 5 days of those workshops, I will try to teach you some fundamentals of quantum computing. As Paweł said, this is an intermediate course, so I hope that you already know some basic of about the quantum computing. And when it comes to the things that we learn, so during our first workshop, we will talk mainly about complex numbers and how do we use them in the context of quantum computing. So during QBronze, you learned how to deal with qubits using real numbers. Now you will learn how to deal with qubits using complex numbers. I might also make a short introduction to quantum gates using complex numbers, and probably just a bit of coding, but there will be more coding during the second lesson. And so if you have some problems with Python or Jupyter during the first lesson, they won't be a big thing. However, I want to warn you that after the second lesson, there will be a coding assignment. So having a working Python environment and being able to download and re-upload IPYNB file is a must. Okay, if there are any questions, please write them in the chat. I hope that our great mentors will answer them. Okay, so let's start. Maybe I will stop sharing the video because I know that sometimes it might be hard for network connection to deal with this. Okay, so let's start. As some of you may know, some maybe not, we have real numbers like 1, 2, 11, like 0.5, which can be written in different forms. It also includes negative numbers like minus 0.2. And there are also imaginary numbers. And the definition of imaginary unit is as follows. we write an imaginary unit as I, and it is equal to the square root of -1. So I to the power of 2 is equal to -1. Okay, and we have also complex numbers, and complex numbers are composition of real numbers and imaginary numbers. So we can have, for example, a following complex number. And here you can see its real part. Let's call it A. And you can here see its imaginary part. And let's call the real number that stands by imaginary unit B. And while 3e is an imaginary number, B, so in this case 3, is still a real number. Okay? And what will be important for us is that we can visualize this complex number. So for real numbers, we can use just a straight line, and we can here like we have here 0, we have here 1, 2, and so on. We have here like, let's say 100, and the same goes in the opposite direction, but with a minus. With complex numbers, we have a problem because we cannot directly see whether, for example, this number, so 2 plus 3i, is bigger than, for example, 2. Because we have here an imaginary unit. So how to at least visualize it? We need another dimension. And this dimension, we will call it, it will be a dimension for the real part, so A. And this dimension will be for imaginary part. So for our part, for our number B. And here we will also write real numbers. So 1, 2, and so on. Let's scale it to 100. And similarly in the other direction. And to visualize this number, we need to trace this real number on the x-axis. So in this case, it will be 2, and the imaginary part on the y-axis. So here, let's say we have number 3. Okay. And we need to trace it down. So here we have 2 plus 3i. And when it comes to qubit, we will also need to change the definition of a qubit that you learned during QBronze. Because if you have a qubit defined using only real numbers, let's call them alpha and beta, there was a condition that if you raise them to the second power and add them up, they need to add up to 1. However, if we have some imaginary unit involved, there we will have a problem, because I squared is equal to -1. So it will change the sign in this equation. So we will have here minus sign, and it won't be sufficient. So we need to introduce something which is called the modulus. And the modulus is interpreted as a distance from the center of the surface. So it will be the length of this line. So how to calculate it? It will be, I think, pretty simple, because you need only here the Pythagorean theorem. And to denote the modulus, we need to vertical lines. So if we have, let's revoke it, z equal 2 plus 3i, we can use the Pythagorean theorem to calculate the modulus. So it will be 2 squared plus 3 squared, and then we need a square root. So it will be 4 plus 9, and it will equal to the square root of 13. So in other words, this line has a length of square root of 13. And what is also you need to know, and I think you already know it, that for real numbers, it's just a real number, but with a positive sign. So if you have, for example, -3, it will be equal to, the modulus of -3 will be equal to 3. And it also tells you the length. So as you can see, the modulus will always return a positive, or at least non-negative number. So it will be also a real number, but non-negative. And if you keep this visualization in mind, you basically don't need to remember this formula and learn it by heart. You just need the visualization and tell yourself to calculate the length of this line. And this way you will obtain the modulus. Okay, so let's come back to our qubit. Oh, we have some connection issues. Okay, so let's assume that we have a qubit, and let's begin with simple cat plus. So something like this. And now let's add an imaginary unit here. And now let's check how we can check if this qubit is a valid qubit. So the length, if we interpret the qubit as a vector, the length of this vector will be equal to 1. So first of all, we have alpha equal to I times square root of 2 divided by 2, and beta equal to just square root of 2 divided by 2. And since we are talking about the length, we will need the modulus. So the modulus of alpha here will be equal to the square root, and here the real part is equal to 0, because as you can see in other words, if we come back to this form, so z equal a plus ib and times b, here we have no real number that is not multiplied by an imaginary unit. So here it will be equal to 0. So let's write it down. 0 squared plus square root of 2 divided by 2 squared. And so this is our b, and as we can refer to this was our b, and this is also our b, this is our a. Let's keep calculating it, and we will obtain, so 0 is just a 0, and here we will get 2 divided by 4, which will be equal to 1 divided by 2, and this we can write down as follows. Okay, so as you can see, once we calculated the modulus, it still seems it seems like we have a cat plus state because we converted it back like to the cat plus state if we calculated the modulus. And if you remember the term local phase, well, an imaginary unit added simply by multiplication of a number inside a state vector representing a qubit is just a local phase. So whether you have a plus or minus or plus I or minus I, it won't affect the probability of measuring state ket0 or ket1 when measured. Okay, and that gives us a hint how to reformulate this condition. And I can tell you that now we will need the modulus squared plus modulus of beta squared. This will need to be equal to 1. So first of all, before you start checking whether a given vector can create a valid quantum state, you need to calculate the modulus of all of those numbers that are inside the vector. So here we calculated the modulus of alpha, then you will need to calculate the modulus of beta, but here you can see that this is kind of trivial, yes, because the modulus of beta in this case will be just beta. Because if you have no imaginary unit and you have just a real number, then the modulus will be equal to this number or minus this number. In this case, we have here no minus, so this equation is true. Okay, so maybe let's give another example. Let's say that I have a quantum state and let it be -1 divided by 2, and let it be I times 3 under the square root divided by 2. And now let's check whether this is a valid quantum state or not. So we have alpha equal to -1 divided by 2, so the modulus of it will be equal to 1 divided by 2. Now, when it comes to beta, we have I times 3 under the square root divided by 2. So the modulus of beta will be again 0. Maybe I will get another example in a minute to have here something meaningful. Plus 3 under the square root divided by 2, and all of it like squared. And it will give us 3 divided by 4, which is again equal to 3 under the square root divided by 2. And now we can check whether this is a valid quantum state or not. So we have modulus of alpha squared times modulus of beta squared, and this is equal to, so we calculated the modulus here, it's 1 divided by 2 squared plus 3 under the square root divided by 2 and all of this squared, 1 divided by 4 plus 3 divided by 4, which is 1. And this way we have checked whether the quantum state is valid or not. And the more elements in this vector you have, like the more elements you need to calculate modulus of, you need to square them and in the end sum them up. So to generalize it, if you have a quantum state where these big N states are possible, you need to calculate the sum of squares of moduluses of those numbers and check whether they all add up to 1. So here it is from 1 to n. Okay, maybe let me give another example, and it will be the last one when it comes to checking whether a given quantum state is valid or not. Let's say I plus 2 divided by 4, and let it be I minus 1 divided by 2. So first of all, let's calculate the modulus of alpha. And in this case, we need to separate the real part from the imaginary part. So I will rewrite it as follows. I divided by 4 plus 2 divided by 4. So here is our A, so the real part, and here our imaginary part, which will be equal to 1 divided by 4. So to calculate the modulus, we need again a square root, and here we have 2 divided by 4 squared plus 1 divided by 4 squared. And so here it will be 4 divided by 16 plus 1 divided by 16. And it all will be equal to 5 divided by 16 under the square root. And when it comes to beta, we can rewrite it as follows. So I divided by 2 minus 1 divided by 2. So let's calculate the modulus. So from the real part, we have minus 1 divided by 2. And whether you include this minus or not, it like doesn't matter, because we have here the power of 2, the second power, plus 1 divided by 2, again squared. Here we will have 1 divided by 4 plus 1 divided by 4, which give us 2 divided by 4. So in other words, 2 under the square root divided by 2. So now let's check whether the condition of this length preservance is met. Okay, so here we have modulus 5 divided by 16. It should be 5. Okay, plus, and here we need a second power, plus 2 under the square root divided by 2, and of course to the second power. So here we will get 5 divided by 16 plus square root of 2 divided by 2. Now we need a common denominator. So it will be 5 divided by 16. Here we need to multiply it by 8. So we will have 8 times square root of 2 divided by 16. Oops. So I believe you can clearly see that this is not equal to 1. It cannot be equal to 1 because here we have a square root. So it will never be equal to 1. So here's an example of an invalid quantum state. Okay, let me check if there are any questions. But if there are, or maybe I simply can't see them, but if there are not,
didn't mm,
Okay,
like earlier. I mean, why it's not 13, 16?
where?
Yeah, because there's a square two. Yeah, and where it's
In
not two square. Yes, later.
uh,
Uh,
Yes, so
I
when
used to
you have
buy.
exactly when
ah
you go to the right, yes.
Yes, that's what I mean. So
5. Here
it
is
should be
5
later,
divided
isn't
by
it?
16 to
The
the
second
second.
part, the second component. So a
Ah,
square over 2 and divided by 2, and then you just
okay. I see. Thanks. Mm, yes, so you are absolutely right. It should be 2 divided by 4. Okay, my bad. Thank you. And here, it should be plus 8, I believe. Okay, so it should be 13 divided by 16, which is still not equal to 1. And is everything okay now? Can you confirm? Okay. So I hear no one protesting, so mm, let's move on. And there is another operation that we can calculate using complex number, and this is its conjugation, and we denote it as follows. So we need a horizontal line above the number that we are trying to calculate the conjugate of, and the conjugate is the okay. So is defined as follows. So if you have a complex number in this form, then its conjugate will be equal to a minus ib. So to put it in some, let's say, more graphical manner, if we have here this real part for A and this imaginary part for B, let's say we have A here and we have B here, and we have our complex number here. This conjugate transpose will only change the sign of B, so there will be a reflection around the real axis. So we will get here. Okay, and it's like it's that simple, I would say. Yes, and one thing to notice that sometimes may be useful is that you multiply a complex number by its conjugate transpose, you should get a 1. So let's check it. We have, maybe I'll write it in another way. So we have A plus IB times A times minus B. We obtain A squared. Okay, maybe so nobody would be too suggestive, and times minus A I B. So the first and the second part here now, second and the first term. So as you can see, like we could also use this formula. it's like x minus y times x plus y, but I want to show you how to calculate it by hand. And now we have minus I squared times b squared. So now we have a squared. Those two elements cancel out, and here we have I squared. And I remind you that I squared is equal to -1, so we are left with b plus. Okay, and if you think about the state vector, so qubit, and try to put the elements that create a complex number as a parts, as a amplitudes, then you can obtain 1. But this is rather a side note. I don't think we will use it much. Okay, let's move to the trigonometry, because as I explained to you already, we can we can visualize our complex number in a two-dimensional plane. And we can simply plug in the real part and the imaginary part. But we can also use something which is called polar coordinates. And if we use polar coordinates, we plug in two elements. The first one is a length of a vector, and the second one is an angle relative to this x-axis. So here we need to provide this length r and the angle theta. And this way we can also describe our complex number. And how to write it down? So I believe that you are already familiar with something very similar from QBronze. And in terms of quantum computing, our R will be always equal to 1, because we will be using a unit circle, or rather I should say a complex unit circle. So if we have a complex number representing a quantum state or an in this case a quantum amplitude, we can write our number as follows. So as you can see, all we need during our quantum computation is this angle theta. And if we want to visualize the whole qubit using complex numbers, now we will need a Bloch sphere, which I will talk about during the second lesson, or two-dimensional surfaces. So the first one will be explaining our local phase, and it will be a unit circle where we will have real part where here is 1 and here is 1, but on imaginary part. Sometimes I've seen also that here is I, simply because simply another convention where here you have 1 and here -1, but in some books I also found there is I and -I. But I will, for now, stick to this convention where we have only real numbers on a drawing, and this will encode only the local phase. So from this part of the drawing, we won't be getting any probabilities when measuring. And for measuring those probabilities, we need a second drawing, which will be much simpler, and it will be something that you already know from QBronze, but simplified just to a quarter of a circle. So let's say if we have a vector that points exactly in the middle of this quarter circle, there we will have an angle theta equal to 45 degrees, or pi divided by 4. And here we will have a local phase. So let's say that we will have maybe, use the red pen. For the beginning, let's say that we will have something rather simple. So a simple local phase. And now we can write our quantum state as follows. So we will have cosine theta, and here sine theta, and here we will have a local phase. For now, I will denote it using lambda, but we will deal with this later. And here we have cosine theta, so it will be a cosine of pi over 4. And here, as you can read from the drawing, it will be I times sinus sine of pi over 4. So it will be square root of 2 over 2 and square root of 2 over 2 times our local phase I. So far so good. And before I introduce you to using local phases that are on this whole complex unit circle, I would like to introduce you to the equation that was voted as the most beautiful equations in mathematics, because it uses all the most important number in mathematics, and it goes as follows. So the Euler number denoted as E to the power of I times pi, then it all plus 1 equal to 0. And here we have like five of the most important numbers in mathematics. We have the Euler number, imaginary unit, pi, 1, and 0. And how to read this drawing and prove to ourselves that this equation is true. And in general, how to read such a number, so an Euler number E to the power of I times something. So if you see something like this, you will need to think about the rotation around the complex unit circle. So we will start from this point, and now we need to draw an angle of pi or other desired angle, but let's start with pi. So let's draw it, and here we have an angle equal to pi, because here we have like pi divided by 2, and here we have pi, and the whole circle is just 2 pi. And if we come back to this drawing, here we have the real part, here we have the imaginary part. So let's write it down one more time. We can read from this drawing that the imaginary part is equal to 0, and the real part is equal to -1, because we have this unit circle. So e to the power of I times pi is equal to -1. So we have -1 plus 1 equals 0. So now let's write down I, so an imaginary unit, using this notation. And for that, we need to decode from this drawing by which angle we need to rotate, starting from this point. Let's mark it in blue, in blue color. We need to find out by which angle we need to rotate from this point to obtain I. So as you can see, it will be pi divided by 2. So let's write it down. If we have e to the power of I times pi divided by 2, so here we have this angle. We need to rotate on this drawing, and as you can see, we will obtain I. And for other special cases, if we have, say, our angle is equal to 0, then of course we have 0, because anything multiplied by 0 is equal to 0, and e to the power of 0 is equal to 1. And so we have already, we have 1, we have -1, we have I, and if you want to have -I, then we will need to, of course, rotate by 270 degrees, or in other words, 3 pi divided by 2. Okay, so let's give another example. Maybe I will start a new drawing. Okay. If I point here, and let's say we have here pi divided by 4. So maybe I write it too low, but let's say we have e to the power of I times pi divided by 4. We can rewrite it as follows. So we will have cosine of theta, so pi divided by 4, plus okay, sorry, let's come back, because I started drawing the whole quantum state. So here we have our real part, we have our imaginary part, and to have a full qubit, we also need a probability that we'll obtain during measurement. So here we have the probability of measuring state 0, and here we have the probability of measuring state 1, and here we have a unit circle or its fragment, then we have an amplitude. So let's say it will be pi divided by 4. Okay, and now we can write our quantum state. Let's call it let's call it C, as follows. So we will have cosine, let's now call it C, plus local phase, so I times theta times sine phi. So now this angle need to read from there, because it determines our probabilities. Pardon, we need also our qubits. So it will be cosine of pi divided by 4 times ket 0 plus e to the power of I times pi divided by 4 times sine of theta. So this part times ket 1. So cosine of pi divided by 4 is equal to square root of 2 divided by 2 times ket 0. And this one we can read from here. And it needs to be equal in modulus to 1. So we will need a local phase where the real part and imaginary part will be the same, because we have here pi divided by 4, which is in the middle between those two axes. And at the same time, it will be equal to 1. And at least in terms of modulus. So, no, sorry. So here we will have I times 1 divided by 2, I think. Let me check it. Okay, sorry for the inconvenience, but I have like a lot of problems with internet connection, I think, today. Can anyone confirm on the chat whether you can see the screen? Okay, that's great. So now let's come back to our example. We have here this e to the power of I times pi divided by 4. And as you can read from this unit circle, it is I plus 1 divided by 2, because everything like here is equal to modulus 1. So we have this number times p squared divided by 2 times ket 1. And this is another way to write out the quantum state of our qubit in form, in an analytical form. And if you want to put it inside the vector, of course we can, because we will have 2 under the square root times 1, 0 plus and here you can see that we have the same number, so they will cancel out, times ket 1. So it will be square root of 2 over 2, here 0, plus here we have 0, and I plus 1 divided by 2. And it all gives us this nice quantum state, but in the form of a vector. So as you can see, we have at least 2 ways to write down the state of our vector. One is a clear vector state, and the other one is an analytical form where we use cosine of some angle times ket 0 plus local phase in this form times sine of the same angle as used in cosine times ket 1. So from cosine and sine, we can read the amplitudes that affect the probability, and from e to the power of I times some angle, we can read the local phase. And one important note is that you can also have local phase here. So let's write it in this form. Cosine, I here used psi, times theta. Sine. Okay. However, we can use a parenthesis here and write down as follows. So cosine of psi plus e, and here, because we are using a denomination to write down our local phase, so we can simply extract this angle. And write it as follows. So as what I wanted to show to you is that here we had 2 local phases, but in the end, only one of them matters. And this one becomes a global phase, and it does not affect the qubit at all. The global phase does not affect the probability outcomes. It does not affect the computational process. It changes like nothing. Even if you have something like phase kickback, which I hope you are familiar with, it won't affect it. Okay. So I think it will be enough when it comes to qubits. Now let's move on to complex matrices using complex numbers. Okay, so today I will not focus on gates, but rather only on matrices that uses complex numbers. So let's say we have let's start with Hadamard gate because I think it's pretty common, everybody knows it. So here you can see that Hadamard gate uses no real numbers. However, we can of course incorporate complex numbers to our quantum gates. And now I want a quantum gate that is similar to the Hadamard gate, but it will change the local phase of ket1 state, not to minus ket, but rather a state where the second element of a vector has a local phase of I, not -1, but I. So I want something like this. Okay, so it almost looks like a ket minus state, but instead of minus, we have I here. And let's us think about such a matrix, which will help us to obtain such a state if we start from ket1. So we will start similarly as in the Hadamard gate, but in the end, we will need simply an imaginary unit. So it will represent the rotation. And what will be important when we start talking about the Fourier transform is the way you act on the local phase. Because we will actually be manipulating it a lot, and if we get to the phase estimation algorithm, we will focus on obtaining a proper local phase. So now I will just multiply it to show you that this we can obtain from ket1, but here it might be something different. So okay, let's simply start computation. I will try to copy it. Okay. Okay. Oh, okay, way better. Okay, so here we'll get 0 plus square root of 2 over 2. And here we will get 0 plus I times square root of 2 over 2. So we get what we want. Okay. What I also want to talk about. Okay, so one of the last things I want to talk before we start coding is the fact that we had some assumptions when it comes to our quantum gates in QBrons. And one of them is those vectors, so the columns of the matrix are linearly independent, and we leave it as it was, so it still applies. However, the second thing was that the elements in each column, or rather the square roots, or wait, no, so the second powers of element in each columns add up to 1. So similarly as we were talking about a quantum state. Let me come back to it. Yes. So during QBrons we have something like this. And now during QSilver we have something like this, and it also applies to the columns inside a matrix. So if I ask you which of the following matrices are valid quantum states, first of all, you need to check whether they are linearly independent, which I hope you know from the QBrons. And the second thing is whether the sum of second power of moduluses of those elements add up to 1. Okay, so here let's continue this example. We have let's check this particular column only, so we will save some time. And so we again have square root of 2 over 2 modulus of it. Then second power, and here the modulus of I times square root of 2 over 2, and the second power of it. So here the modulus does not change the number. Okay, to the power of 2 plus, and here, if you remember correctly, it will be square root of 2 over 2. So now we will have 2 over 4 plus 2 over 4, which is equal to 4 over 4, which is 1. Okay, and the second, the same thing we will do for the first column. And if we have more qubits, let's say we have a matrix, a quantum gate that operates on 2 qubits, then we will need a matrix that will be of dimension 2 to the power of n times 2 to the power of n, when n is the number of qubits. So here we have n equal to 1 because Hadamard gate and also this gate where we have this imaginary unit operates on 1 qubit. If we have 2 qubits, we will have here a matrix 4 by 4. For 3 qubits, we will have 8 by 8, and so on. And we still need that the sum of the second power of moduluses in each column add up to 1. Okay. So now I would like to move to some coding. However, it won't be notebooks, but some code about complex numbers. So I will share my screen in a minute. Okay. Share. Okay, and you should be able to see my empty Jupyter notebook. So let me define a complex number. Let's call it Z. And if you have a real number, you just write a real number. But if you have a complex number on any kind of imaginary number, we need to add up the imaginary part. And in Python, it's denoted by J. by j. Okay. Okay, the connection should be okay. So we have 3 plus 2i, but in this case, in Python, we denote it differently. So now let's create it and let's print it. So as you can see, this letter is not interpreted as a variable. It's a complex, it's an imaginary unit in Python, so it's not denoted by. Of course, we can add imaginary units and complex numbers, and we can also calculate the conjugate of an imaginary number, and we do this by using something which is called a method. And a method is a special kind of function which is assigned directly to the object, to the class. So we will call it the following way. Okay, so as you can see, we have calculated the conjugate of variable z, which is equal to z, but with a negative sign, or the opposite sign on the imaginary part. And if you want to write a single imaginary unit, you can't simply write j, because you will have Python will think that this is a variable. You need to write something like this. So simply one j. Okay, and sometimes we will be interested in extracting only the real part of our complex number, and for that we need to call an attribute of this complex number simply by typing z.real. And as you can see, it is a float, so it's 3.0, it's not 3, because a complex number is more complicated even than a float, and Python, when getting the real part from the complex number, will always return float. Okay, so we can also get imaginary parts, so we need to simply call the IMAC attribute. Now let's write a formula for modulus. For now by hand, so rather without using pre-programmed functions. So as you can remember, we need our A, so our real part. We need second power of it. And then we need our imaginary part, and its second power, which we denote as follows, and then we need a square root. So this is our modulus. However, we can also use a pre-programmed function, and for that we need to import NumPy, which is an external library. And when installing Qiskit, I believe that NumPy should also be installed together with Qiskit and Circ. Okay, so let's, okay, I will import NumPy as P. And you can see that we get the same result, both by programming it manually and by using a pre-programmed function. Okay, now let's recreate the most famous equation in mathematics. So we will need an Euler number, so E, and it's pre-programmed in the NumPy library as well, so we can call it this way. So as you can see, this is the Euler number. Then we need to raise it to the power, and what power? So we have this imaginary unit, which we write as follows. And then we need an angle, some kind of write it in a form of pi divided or multiplied by something. So not by using angles, but rather by using radians. And we can also refer to pi using NumPy library simply by typing numpy dot. So here, as you can see, we take -1 plus something, but if you look closely, it is extremely close to zero. So this is only because of the rounding accuracy and the precision of our computation. So we basically cannot do much about it. So let's round this number. So we will have simply -1. And here I think there was some kind of a problem in one of the notebooks, but I think it was only in the Qiskit, so this in that notebook where there's a problem with rounding. Because if we try to round a complex number, we will get a type error. However, we can round its real part, and we can also round its imaginary part. So as you can see, it's pretty straightforward if we call this z variable. So now let's write this formula in a way that our result will be more neat. So we have NumPy. From NumPy, we have the Euler number, the power of imaginary unit times pi. And let's say that we want to get an imaginary part of this number. Okay, so we have, and it's really small, it's like this number divided to the 10 to the 16th power. So 10 to the 16th power is an extreme big number, and if we have it in the denominator, then we obtain a small number very close to zero, and we can now round it safely. So we get this imaginary part equal to zero. Maybe I will add some zero, so we can see that it's still zero. And to get the real part, both real and imaginary part from this expression, because we have something like this, let me declare a new variable where I will store the real part. Okay, no bugs. And the second variable where I will store the imaginary part. And our final number, but rounded, so we won't have this not so nice looking long string of numbers. We'll use here a round function. Our imaginary part was also rounded. Let's say 3 places after the decimal point. And okay. Here we have this. I believe that I'm not quite sure where I did the mistake. Here's the chart.
I think you should add the additional braces around numpy is to the power and for imaginary part.
Okay. Yes, thank you. That was my mistake. So rather a rookie mistake. And now it should work just fine. And here maybe for some to make it clear, let's get that we have this real, this imaginary unit. Okay, so thank you for your help. Okay, so now I want to write a function that will check whether our qubit is good or not, so whether this is a valid qubit or not. So let me declare some qubit, but so far in the form of a list. And let it be, let the first term be imaginary unit -2, it all divided by 2. And the second part of the qubit, let it be -1 divided by square root of 2. And let's print it. Print. Okay. So we want to calculate this sum that we are talking about. And for that, let's initialize it. And then let's write a loop where we will iterate over the elements of this vector. So we have our qubit, which we called sum qubit, and we will calculate the sum such a way. Of course, we can write it shorter, but I don't want it to be too hard for people that are not like programmers. And for that, we need to calculate the modulus squared of each element. So we can use already the function that calculates the modulus from numpy. And then once we calculate the modulus, we need to square it. And now let's check whether the length of our vector is valid or not. So length of the vector will be equal to the square root of our sum. But if it's, and we expect the sum, the square root of our sum to be equal to 1, but if we expect the length of our qubit to be equal to 1, then of course, if you have the square root, it will also be 1. And as you can see, it is not equal to 1. Okay, so maybe let's try another one. Okay, so let it be okay, you should kill me again. Okay, now let's test 2 times 2 plus 1 imaginary unit. It all divided by, let's say, 4. And the second part, let it be square root of 3 divided by 4. It will be another qubit. So we declared it, and now we can also calculate its length. And as you can see now, this time it's short. So you can like write your own function, you can wrap it inside the function, and it is not necessary to pass the assignment, and I believe you can do it by hand. However, I only wanted to show you like those function in action. And there is still one thing that I think I haven't covered yet, but you will need it for the quiz. So now the one who listens will know what's inside the quiz. And okay, we have a question: should we also add additional real in the previous example? So we have real equal to -1. I'm not sure in the previous example if we are yes, you are absolutely right. We should add also parenthesis, so to be -1. So I skipped it. So thank you for this information. Okay, so yeah, here I made a mistake. Like I like it was exactly the same mistake that I made here. Like I need another parenthesis because I simply get the real part out of pi. Okay, so now let's create some random qubit. And of course, you can get your alpha and beta. You can like choose it randomly. However, I encourage you to use angles. So this notation that uses angles, because once we started using the complex numbers, trust me, you will have much less work to do because you have already the standardized form of the local phase, which will be extremely useful. So now let's calculate the angle corresponding to the local phase. Let's call it local phase angle variable. And let's choose it randomly from the uniform distribution. And I will explain why from 0 to 1 in a moment. And also the number alpha is also from the same uniform distribution. And why I want to sample from the uniform distribution from 0 to 1, because I want to treat the whole unit circle as 1. So the whole rotation should be 1. So now to calculate the local phase itself, let's write it in a following form. So now the power of e times 1 imaginary unit times this angle. Or maybe for the sake of, I think that it will be easier to understand maybe if we have here like 2 times pi. Yes, I believe it will be much easier to understand now. Okay. So now we have, so here we are sampling the angle. Maybe I will not treat it as the whole rotation as 1, but rather as 2 pi, because now I think as I started explaining it in that way, maybe it will be easier to sample something from 0 to pi. And now let's calculate the local phase here. We have here, and to get this representation of this qubit, some random qubit, we can calculate the cosine of alpha, and maybe alpha will sample again from pi over 2. And here we use alpha, and here we will use our local phase times sine of alpha.
Yeah, there is a typo in the second line. Uniform instead of uniform.
Okay, uniform, and here. Okay, thank you. So we have here our random qubit. Okay, and here we have also still no, okay, it should be okay, I believe. Or is it too long? No, I believe it should be okay. I will double check everything before I send it on Discord. Oh, so I have some problems with the microphone. Okay, and the last thing that you will find inside your notebooks will be calculating the polar form of a complex number. So let's say we have a complex number z equal to minus 3 imaginary units. And as I hope you already know, it should be equal to the modulus of this number, which we are how to calculate. Okay, no errors. However, we will have it might be a bit trickier to get the angle, and we will be only interested in the angle in the first quarter of the unit circle. And for that, we can use an inverted sine function, which is called an arcus sine or asine. So let's get it. We can use a sine function here, and for that we will need a part of our number which corresponds to the imaginary part. So let's come back to OneNote. Oh, from this representation, so we will be only interested in the imaginary part. So let's calculate it. So it will be minus 3 divided by r. And so now we have the length, and also we have the angle. So let's bring the results. So we have the length is equal to r, and we have the angle, which is equal to alpha. Okay, so I believe that let me check if we have anything more on our agenda. Oh, one more thing, a scalar product. So it will be the final part of today's lesson. So calculating the scalar product, and the scalar product of a vector. Let's say we have a vector that we denote this way. To calculate it, we need to write something like this. So this notation denotes the scalar product. Sometimes it is denoted this way, but both notations are correct. And to obtain,
You're still showing the Jupyter notebook.
can you hear me?
Yes, we can hear you, but you're still showing the Jupyter notebook. You probably showing something on the environment.
Okay. Okay, you should be able to see my OneNote. Can you see it?
Yes.
Okay, thanks. So I will start maybe one more time with this. So let's say you have a vector or a qubit, and if we have interpreted as a vector, we might want to calculate its scalar product. So which we will write as follows. So here you can also have one line, you have two lines. It doesn't matter. It's just a matter of notation, as I already said. So both notations here are correct. And to this, we already have this vector here, like this, what we started with. And to calculate this vector, we need to take the complex conjugate of the vector that we started with. So let's say that if we have our, let's say, vector for two states, so a single qubit vector, we could denote it as follows. Okay. So use here this rectangular form instead of polar form or anything like that. And its complex conjugate would be just complex conjugate of all of its elements, which we can write as follows. So here we need this horizontal line, and here we also need this horizontal line. A minus imaginary unit times b, and c minus imaginary unit times b. Okay, and then we just simply need to proceed with the multiplication element by element. Okay. Again, I have some problems with this connection. Okay. So we will need to multiply those elements. A times A minus imaginary unit times B, C minus imaginary unit times D, and now we can use a simply different notation for the scalar product. So we'll use it as a normal regular parenthesis, because we simply can do that because we are not we don't need to talk about quantum. We can, but we don't need to because we have mathematics. Now, what we need to do is to multiply it element by element. So okay, I believe I again have some problems with internet connection because I believe you couldn't hear me. Now I can't see anything. Okay, now it should be okay again. So to calculate the scalar product, we need to multiply the elements in each vector's element by element. So it will be A minus imaginary unit times P, and then times another parenthesis A times A plus imaginary times P. And here we need a summation sign, and we'll again multiply those two numbers. And that's it. And we can, of course, get inside of those parentheses, but I believe this is just clear arithmetics, and I think you should be able to do that easily. And so I think it will be all for this lecture. I will only show you maybe which of the notebooks you are expected to browse through. And for that, I again need to stop sharing, and let's get here, and let me share my screen. So yes, the Qiskit introduction. If you have forgotten all the Qiskit, I would advise to browse through this first notebook. And the notebook about the complex numbers is more or less what I have already explained. However, if you need another explanation, I think it's good to get there. Mathematical notations, I think, too. Quantum state with complex numbers. This one, let me just open it. Here you will get a very similar exercise to what we've been talking about, like in the end of this lesson. So creating a random state, quantum operator with complex numbers, So here you will have more information about the gates. However, I do not expect yet to know different named quantum gates that uses imaginary units and complex number. We will learn more about the quantum gates that use complex number during the next lesson. So for now, I only showcased the matrices that use complex numbers. And for the first lesson, I think it should be okay. However, when it comes to some named gates, I do not expect it yet to know everything. So C03 is okay to do today. However, C04 we will do during the next lesson. Global and local phase we already talked about it, and about the state visualization. You will get like those circles that I have drawn in OneNote, and also the conversion from polar to rectangular form. So this trick with Arcus sign. And that's all from me for today. I will stay if you have any question. I will also upload this OneNote. I'm not sure whether today, maybe tomorrow, and also this notebook where I was live coding with you. But only once I check whether there are any errors. I hope that next time I will have better internet connection. I believe that while the screen was doing okay, but sometimes my microphone, I think, was cutting off, and I also got a lot of notifications about the state of my internet connection. So I hope that during the next lesson it will be okay. So thank you for today. And if you have any questions, you can text me on Discord, or you can basically ask those questions on those open channels.
Okay, thanks, Przemek. Thank you.
Thanks.
Let's see. I see that there are some questions on the chat. They were asked in the meanwhile when I was not present, so I'm not sure if you have answered already. If not, you can.
Oh, I see that there is a note about the dot product and the scalar product. I should maybe mention about that in some countries. I know that those two terms can mean sometimes something different. But I see here that the discussion already arose. Okay.
Okay. Do we have more questions? And I've sent invitations to Canvas to all of you, or to all people who have registered and are invited for our workshop. So please check your mailbox. If you cannot find the Canvas invitation, please send me a message. And I think this is all. So in Canvas, you should be able to see the first quiz. As far as I remember, the deadline is in about 2 weeks from now. All right, and the next session will be on Thursday, as announced on February 26th.
Excuse me, Paul, just a question, please.
Yes.
If we finish that course on the Canvas, will we get a certificate?
Yes. So as was mentioned on the slides, and you will also find it on Canvas and on the website, you need to get at least 50% of the points from each homework, and at least 70% together from all homeworks, quizzes, and assignments. So this is a requirement.
Yeah, why I'm asking, because I finished previous courses on a similar one, but just being graded with excellent marks, but I don't know how to get the certificate.
Was it QSilver as well?
Yeah.
And
On the
do you know
keyword, yeah.
keyword, and do you know who organized it? Who was the
No,
organizer?
it was not you. It was like a Q Tunisia, for example, some other parties. Yeah.
It is, and do you remember when it was exactly? Was it just last
Yeah, I
month
just
or?
I can give you some if that is okay. I can give you some of them.
Okay, just send me a link, or I will try to find the event page on the Keywords website. It should be there, I believe. Let me
Yeah,
check
I
it.
mean, just when you finish all the quizzes, 5 or 4 quizzes, then you get it graded. But there is no
Okay.
option to get, yeah, like for
Uh,
example,
so
Q bronze 175, Q bronze 180. Just an example.
you should receive a diploma. So let me just check the website. Okay.
Yeah.
So you should contact the workshop organizers because this is their
Okay.
responsibility. Q Tunisia and Q Egypt, right? You can see the instructors and you can see the email addresses. So please contact them because yeah. So this workshop was just quite recently, February 9 to 12. So I'm pretty sure that they still need time because in our case you will not get a certificate immediately,
Yeah.
right? As far as I remember, the deadline for the last assignment is March 20th,
Yeah.
right? And then we usually need about 2 weeks to prepare, process, and send the certificates. So you will
All right.
get the certificate. So if you pass all the quizzes and assignments, you will get a certificate from us around April. And I believe that this workshop just finished about 2 weeks, 1.5 week ago. So I believe that they
Okay.
will also send you the certificates around end of March or something like that.
All right. Okay. Thank you
Okay.
very much. Thank you.
All right.
Dziękuję.
But if if
Dziękuję.
if but if not, then just please send an email to the organizers. And it's the same with the other workshops because I see that someone mentioned about QWord 173, QBronze 173. So please let me check it when it was organized. So it depends on the organizers. So some organizers are quite fast, some are quite
Yeah.
slow. It also depends on our graphic designer. So she also
Yeah.
needs time. So the Q Bronze 173. Honestly, I do not see a website, so I'm not sure who was the organizer. Let me check
Yeah.
because we
Yeah.
should have
Yeah.
it in our records.
Yeah.
We should have it
Okay.
in our archives.
Yeah.
Q Bronze 173. Because I see this question here on the chat. It was
Yeah.
organized by QCheck.
Who's
Uh,
that? Who was the organizer?
from Czech Republic, our quantum cousin
Czech Republic. Yeah.
our quantum cousin from Czech Republic. You
Yeah.
have to contact them by email directly. It's their responsibility to to send you the certificates.
Even the recent one, Q bronze 180 and a Q bronze 58. I finished 4 or 5 of these. Uh, I mean, these courses on Canvas, but never get any certificate.
Uh, if you can, please send me information on Discord, okay, about the numbers of
Okay,
the
Paul.
workshops because I can also try to contact the organizers and ask
Thank you.
what
Thank you very
happened.
much.
Because
Thank you very
sometimes it takes time, but usually the certificate should be sent in up to 2 months after the workshop.
All right. Okay. Thank you very much.
Okay, thanks. Okay, thanks. Okay, good. Thank you. Is there anything else you would like to know? Do you have more questions? If not, then we thank you for participating today. The next session is on Thursday. You can already start working on the first quiz. As far as I remember, you'll have 3 attempts and the highest score will count. And if you have any questions, please ask your questions on Discord, and our mentors are here to answer your questions and help you. Thank you. Enjoy. Have a good evening. Bye bye. I will stop recording now.
Thank you very much.